In this video, we'll be looking at a few more pharmacokinetic concepts. Here are the learning outcomes that we'll be looking at in this video. So to start off with, we're looking at bioavailability, and we'll start with absolute bioavailability. So what we're comparing here is the amount of drug that gets into the body via the intravenous system, where all of the drug gets into the systemic circulation, and compare it to some sort of other formulation, whether that be an oral tablet or a capsule or a suppository or a topical transdermal patch. And so if we inject the drug into the body, what will happen is that you'll end up with this nice kinetic curve. And if you take an oral formulation or a transdermal, you'll end up with a slightly different curve where there is an absorption phase and an elimination phase that is obvious in the kinetics. Now, to compare these two together, what we're going to look at is actually the area under the curve. So the area under the curve, which is an indicator of drug exposure, is measured. Usually something like a trapezoidal rule would be sufficient in this kind of case to determine the area under the curve for the intravenous dose, and the same is done for the oral dose, and these two are compared. And generally, the oral will be slightly less than the IV, and so you will end up with a fraction, sometimes it's expressed as a percentage, of how much drug actually gets into the systemic circulation. The next part is looking at relative bioavailability, and this allows formulations of the same drug to be compared to each other. So if two tablets are on the market for the same drug, and the PBS would like to know whether these are equivalent or bioequivalent to each other, i.e., can they be substituted one for the other and the effect be the same for the patient? And so there are a number of different factors that can be looked at. So if we take one drug formulation and compare it to another drug formulation, are they close enough to each other to be said, yes, they are bioequivalent? And there are a number of points that can be looked at. So area under the curve is one example. So you can compare the area under the curve. You can look at the time to the maximum dose, and you can look at the Cmax, or the maximum concentration, or where that peak is. And if all of those are within, say, about 10% of each other, then the tablets, in this case, are bioequivalent to each other, which means that the patient can expect the same response regardless of which formulation they are actually taking. Okay, the next concept I'll introduce is referred to as the apparent volume of distribution. Now, it's apparent because it doesn't always map nicely with the volumes that we expect to see in the body. So when they're small, they seem to make sense. They might be small and close to plasma levels, around the 5 litre mark, or maybe a bit less. But as they get bigger and bigger, around the 20 and 40 litre mark, you can see that the drug is diffusing into more and more tissue space. And that's really what the apparent volume of distribution is used for. However, when you get round figures of like 100 litres, you go, well, how does 100 litres fit into a 70 kilogram person? It just doesn't make sense. They're not a TARDIS. So it actually is about tissue distribution. And so what that actually means when they're really large volumes of distribution is that it is predominantly made it into the tissue space, and it may actually have a greater affinity for the tissue space and get stuck there a little bit. And so when you test the plasma levels, you find that most of the drug's not there. It's actually somewhere else in the body. So the equation that is used to calculate the apparent volume of distribution is basically the amount. It's a concentration equation, essentially. It's the amount, or the mass, divided by the plasma concentration, and that will give you an apparent volume of distribution. Now, the amount is usually, it could be moles, milligrams, grams, something like that, divided by whatever is found in the plasma. So if we have a look at an example of that, say the person is given 10 moles or 10 grams if you like, and when you test the plasma, you find there's 2 moles per litre. And so therefore, if you put your 2 moles per liter in your concentration mark, and you know that 10 is the quantity that you gave them, then 10 divided by 2 will give you 5. So the volume of distribution is 5. But what happens if some of the drug diffuses into the tissue space? And I resample again, and the plasma concentration says now there's 1.2 moles per liter rather than 2 moles. And I do the calculation again, I end up with 8 liters now. So the 8 liters is telling me some of that drug is now in the tissue space. And if we take it a step further, and more of the drug is now in the tissue space, and I do a plasma concentration check, and I get to 0.6 moles per liter, then if I do the calculation again, 10 divided by 0.6, I'll end up with 16.6 liters. So you can see the volume of distribution has increased yet again as more of the drug is found in the tissue space. And finally, we can take that even further with a plasma concentration of 0.2, and we end up with a volume of distribution around 50 liters. So most of the drug now is found in the tissue space and not very much is found in the plasma itself. So what does this all mean? So with very small volumes of distribution, less than 5 liters, the drug is mainly in the plasma. It may be really heavily bound to the plasma proteins like albumin or something like that, or it may have a really high molecular weight, and so therefore it doesn't diffuse and cross membranes or move through cell junctions particularly well. However, as the volume of distribution increases, then you'll find the drug residing in extracellular fluid. It doesn't have particularly good lipid solubility, but it's still enough to get out of the plasma and into the tissue space. And then what happens next as the volume of distribution is bigger again, what you'll see is the drug can also be found in the intracellular fluid. So it's now can be found in the plasma, it can be found in the extracellular fluid, it can be found in the intracellular fluid. And it usually has very good lipid solubility at this stage because it can actually diffuse between the lipid and the cytoplasm quite readily. And then when we start to look at volumes of distribution greater than 40 liters, so what we're going to see now is the drug is starting to distribute into other compartments and maybe have a higher affinity for those compartments. So if the drug's very lipophilic, it might go into the fat or the adipose tissue, or if it's like a bisphosphonate that's used for osteoporosis, then it might have really strong affinity for calcium in the bones. And so just as a side note, to explain these volumes of distributions are around for a 70 kilogram person. A lot of the time you'll see volumes of distribution, particularly when they're literature volumes, it'll be per kilogram, so it'll be liters per kilogram. So the volume of distribution can be calculated from a person's weight. Okay, the next concept we'll be introducing is the steady state concentration. And I'm going to be using an IV infusion just to kind of explain what's going on. So an IV infusion is an intravenous delivery of drug at a constant rate. So instead of being a single bolus injection, one-off kind of thing, this is a constant infusion of the drug over time. And so as you alter the infusion rate, so you speed it up or slow it down, therefore the amount of drug delivered changes. And the body adjusts to the speed of that infusion. If the infusion rate is low, then the steady state is lower, and if it's a higher one, the steady state is now higher. And the time to reach that steady state is about 4 to 5 half-lives. Now, if you haven't bumped into half-life before, then it's the time taken for the drug, usually when we're talking about elimination, to drop from where it's now to half its concentration, and that time is referred to as the half-life. So it takes, as I said, 4 to 5 half-lives. Now, in the first half-life, it'll reach about 50% of the steady state concentration, then up to 75%. So you can see it's only gone it's gone halfway to the next point, and then it goes halfway to the next point and halfway to the next point. And so that's what we're looking at here. So we're seeing a half, then half of a half, and then half of a half of a half. And so that's the way these drug accumulation curves look and the way they behave. The other thing I'd like to point out now is why the steady state is important. And it's important because what we're trying to do is get the steady state into the optimal range. This is sometimes also referred to as the therapeutic window. And we'll just use the plasma concentration as that target. There can be other targets, so it could be an area under the curve target, it could be a Cmax target, or it could be a Cmin target that is defining your optimal range. But for the moment, we'll look at plasma concentration. And so you have this minimum effective concentration. And so we want the plasma concentration to be above that point to actually see a therapeutic effect. And we also want it to be below the maximum safe concentration, because above that, the patient is more likely to experience an adverse drug reaction. The next point that I'd like to explore now is the idea of multi-dose pharmacokinetics. So we've got the curve on the screen that we've seen before, the IV infusion, which is just a constant rate of drug infusion. But when you start looking at multi-dose, so particularly people that are in the community will be taking tablets. They don't walk around with an IV infusion bag all the time. And so therefore the kinetics looks different, because you'll end up with a bolus and then it'll eliminate, and then the next dose is given. And so you see this sawtooth kind of behavior. But the shape of the curve follows the IV infusion curve. So just like in the IV infusion curve, you're also going to see that accumulation rate until the amount in equals the amount out. And so we can still get a steady state. So in this case, the average concentration is going to be the steady state. And we still need to consider the maximum safe dose and the minimum effective dose to make sure that the amount of drug in the patient is actually being effective and not harmful. The next point that I just wanted to pop up there was the Cmin. Now this is something that you'll see when you're using multi-dose pharmacokinetics that you really don't talk about as much when you're talking about a single dose. So the Cmin is this trough concentration, which occurs just before the next dose. So each one of these is a Cmin. Now, in the steady state, your Cmin will be more constant than the initial kind of phases in those first 4 to 5 half-lives. The next point I'd like to introduce is the idea of a loading dose or loading doses. So this is where the dose is usually larger than your maintenance dose. And the point is that you get to your steady state concentration faster than you would if you gave just the maintenance dose. So you can see that the dose here is much larger and eliminates at a faster rate and then gets out. And then if we swap over to the maintenance dose, you can see that we are now in the therapeutic range. Whereas before, on that second dose, we were just getting into it, but you can see we're well into the therapeutic range on the second dose if we used a loading dose. Now let's talk about how drugs behave once they're in the body. Now sometimes it's fairly simple, and essentially you can treat the body like a bucket. And so you have just one volume of distribution where all the drug goes, and all the kinetics around that behave fairly simply and can be explained with a single compartment. So the drug can be delivered through the gastrointestinal tract and absorbed, and the rate can be observed with this K absorbed. And the elimination rate is a summation of the excretion and the metabolism of the drug from a single compartment. And generally that will behave like in the following illustration. So the IV curve is just all the way out, and the oral dose is going to be, there's going to be an absorption phase and there's going to be an elimination phase. And this is classic of your first order behavior. Now, when you're analyzing that kind of behavior, what's actually important, particularly if it's first order, is that if you log the concentration. So if you take a natural log of the concentration, what you will observe is that you end up with a straight line. And so this is really almost diagnostic of a first order behavior. So if I log the concentration of say just the IV, I'll end up with a straight line. The oral one is a little bit more complicated, but eventually you'll get to the elimination phase, which will be a straight line. Now, if we have a look at some other drugs, they don't behave exactly the same way. And this could be explained by a two-compartment model. So we're talking about volume of distribution, where the volume of distribution was quite large. And so this might occur more frequently in drugs with high volumes of distribution. So we've got the same bucket principle here, which is our central compartment. The drug goes in through the gastrointestinal tract or maybe IV into the central compartment. It still has its absorption rates and its elimination rates, but there's now this second compartment. And it has its own kinetics. So the amount of drug going into it and the amount of drug coming out of it is dependent on the affinity of the drug for that compartment. And so when you explore the behavior on a concentration time curve, it behaves differently. And so what's happening here is that the kinetics are being affected by that second compartment. So the first compartment might have a very fast phase for elimination because all the elimination is occurring through the central compartment. But the beta phase, or the slower phase, happens as the drug slowly comes out of that second phase into the central compartment. But because it does this at a slower rate, it slows the whole system down, and it can start to be seen in the kinetics. So some drugs may have a very rapid elimination phase to start with, but then they start to slow down as the drug that's now in the second compartment is taking its time to get out of the second compartment. All right, so back to the learning outcomes. So you should be able to calculate the bioavailability of a drug using area under the curve values. You should be able to calculate a drug's apparent volume of distribution based on plasma concentrations and the amount of drug that is being used. You should be able to predict the drug distribution based on its apparent volume of distribution, so very small ones being trapped in the plasma, and to the other extent where you have very large volumes of distribution where you're starting to get high tissue affinity for certain tissues. Should be able to explain when a steady state concentration can be reached, so when you're balancing the ins and outs, and also how long it takes to get to that steady state concentration. Also be able to outline when a loading dose is used and what its benefits are, and differentiate drug behavior in a one-compartment model from a two-compartment model where there is a second compartment which can affect the elimination, so you have that alpha and that beta phase.